students, today we are going to discuss about 1,3-dipolar cycloaddition reaction. So it is mostly resembles with Diels-Sutter reaction. You can see in case of Diels-Sutter reaction, we react diene plus dienophile and we will get a final product, that is a cyclic compound, right? In case of this also, as a name it suggests, only it is a 1,3-dipolar cycloaddition reaction. So there is one system which contains 1,3-dipolar system, means there is a dipole present in that system. Suppose we have this A, B, C type of system, 3 atoms are there. So in case of this A, B, C, if A containing a positive charge and C containing a negative charge, so at 1 and 3 position there is a poles, different poles are there. So it is a 1,3-dipolar system we have. This one is a 1,3-dipolar system. And the second one is, as in case of Diels-Sutter reaction, we have this diene plus dienophile. Now we have this diene type of compound, that is 1,3-dipolar system. Then for case of this dienophile, we have here, that is X double bond Y. Suppose one alkene type of system, we can call it as a dipolarophile. Dipolarophile. As in case of Diels-Sutter reaction, we said it is a diene plus dienophile. Then if it is a 1,3-dipolar system, then 1,3-dipolar plus dipolarophile. Now this is also one concerted reaction, as it is a pericyclic reaction. You can say this is a concerted reaction, concerted type of reaction, and you can say it is a 4 pi plus 2 pi cycloaddition reaction. Okay, 4 pi plus 2 pi cycloaddition reaction. How it is so? See, if we have this type of compound, that is A, B, C, A containing a positive charge, C containing a negative charge, then this middle atom, that is B, suppose it contains lone pair of electrons, this electrons will shift here, then you will get this A double bond B, C containing negative charge. So this 2 electrons from this pi bond and 2 electrons from this negative charge. So totally we have 4 pi electrons, right? As this whole system, that is 1,3-dipolar system containing 3 p orbitals. So totally 4 electrons are distributed among these 3 atoms. So we have 4 pi electrons from this 1,3-dipolar system, and we have this dipolarophile. So the dipolarophile contain 2 electrons, right? 2 pi electrons. So this 4 pi plus 2 pi cycloaddition reaction. We are going to do cycloaddition reaction. Okay. So totally this system is 4 pi plus 2 pi cycloaddition type of reaction. Now in case of this 1,3-dipolar system, here in case of this 1,3-dipolar system, these 3 atoms may be different, maybe carbon, maybe nitrogen, maybe oxygen, depends on the condition or depends on the compound. See, in case of this 1,3-dipolarophile, if the species A here, which contains a positive charge, then in case of a B and in case of a C, this atoms may be differ. So this A containing a negative or positive charge, it will be different. So if A has a 6 electron, mostly some assumptions where A has 6 electrons, then as it containing positive charge, this C containing a negative charge. So A containing 6 electrons, B containing its completed octet, and also C containing its completed octet. Means in case of A, its last or valence electron shell containing only 6 electrons. So that's why it is positive. Then B containing 8 electrons and C containing 8 electrons, but C contain negative charge. And in case of this B, there is one lone pair of electron, means one lone pair is must here. At least one lone pair should be here in case of this middle atom, that is B. Now in case of this A, B and C, A may be a carbon or oxygen or nitrogen atom, then here B may be nitrogen or oxygen atom, and C may be carbon, nitrogen or oxygen. So there is a difference, just only that middle atom will be carbon or oxygen, nitrogen or oxygen, not be carbon. Now in case of this, if this B atom, in case of I am talking about only B, if B is nitrogen, then only single bond or double bond is present. If there is B is nitrogen, and if B is oxygen, then only single bond will be present. If B is nitrogen, then single bond or double bond. Single bond or double bond possible. Then in case of oxygen, only single bond is possible. As it is a middle atom, you can say as it is a middle atom, if there is oxygen, then only single bond is preferable, and if it is nitrogen, then single bond or double bond is preferable. So this is important points about 1,3 dipolar system. A containing 6 electrons, B containing 8 electrons means completed octet, C containing 8 electrons means it's also have completed octet, but A containing positive charge because of it containing 6 electrons. Now B must contain at least one lone pair, and C having a negative charge and A having a positive charge. So A may be carbon, oxygen or nitrogen. Also C may be carbon, nitrogen or oxygen. But in case of this B, it may be nitrogen or oxygen and not a carbon. Okay. See some examples. If we have this type of system, that is carbon, double bond nitrogen, oxygen. This oxygen containing lone pairs and having a negative charge. This carbon will contain positive charge. Now the system may be in resonance. So you can say carbon having triple bond, positive charge will be here, and here will be negative charge. As this nitrogen having at least one lone pair, right? This middle atom, that is B, if there is a nitrogen, it can create a single bond or a double bond, as well as it must contain one lone pair. The middle atom must contain lone pair. So if we have this nitrogen, it has one lone pair, it can easily donate its lone pair, means share its lone pair here. So finally it will become a 3 bonded system and nitrogen containing positive charge. Now this system is, we can call nitrile oxide. Nitrile oxide. Now check if nitrogen is the middle atom. If we change the atom, suppose oxygen as in middle atom, here carbon, then oxygen, then suppose carbon, positive, and here we have negative. Oxygen must containing 2 lone pairs. Then in resonance it will be carbon, carbon, double bond oxygen, carbon, negative charge. This lone pair will shift here, so here will be a double bond. Now this oxygen may contain positive charge. This type of system is called nitrile, or sorry, carbonyl imides, right? Carbonyl imides. So this is the when oxygen is the middle atom. Then secondly we can say, suppose we have a ozone system, oxygen, 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 right? O3 molecule. This oxygen means contain positive charge, this will contain negative charge, and middle oxygen containing a 2 lone pairs. So after resonance you can see the structure may be as per this: oxygen, double bond, oxygen, double bond, oxygen, positive charge and negative charge. Okay, so this type of systems, it is called 1,3 dipolar system. At 1 and 3 position there is a dipolar, or 2 poles are there. So see, this is a 1,3 dipolar system, and in case of this alkene or dipolarophile system, it may be a simple alkenes or alkynes or imines which containing a double bond, or simple carbonyl compounds will be there. So this is a 1,3 dipolar cycloaddition reaction where 1,3 dipolar system reacted with or going to add with a dipolarophile. So next point is the stereochemistry of 1,3 dipolar cycloaddition reactions. As we have already discussed that these reactions are resembles with Diels-Alder reaction. So the stereochemistry of this 1,3 dipolar cycloaddition reaction is analogous to that of the Diels-Alder reaction, and hence it is stereospecific. That is, as Diels-Alder reaction show you syn cycloaddition, this 1,3 dipolar system also give you syn system or syn cycloaddition reaction. We have this A, B, C system, A, B and C containing negative charge, that is a 1,3 dipolar system, and X double bond Y, that is a dipolarophile. So in this transition state, A, B and C will be there. As this C will attack here, it will make a new bond between carbon and this Y atom. This electron will shift here and will make a new bond between X and Y, X and A. So here in transition state you can say A, B, C, and here we have X and Y, right? So there is a new bond will form between these two atoms. This double bond will break down and this new bond will form between these two atoms. So finally we have this product A, B, C, 5-membered ring, X and Y. This is your final adduct we are getting. Now this is a syn addition when both 1,3 dipole and dipolar file are symmetrical or unsymmetrical. There are two possibilities about the orientation for the addition, that is two isomeric products are formed. Okay, then both steric and electronic factors play important role in the determination of the stereochemistry or regioselectivity of the addition, and it's mostly depend about the frontier molecular orbital theory. So just go for this FMO theory, frontier molecular orbital theory, and in this theory we discuss about HOMO and LUMO, that is highest occupied molecular orbital and lowest unoccupied molecular orbital. So we have a system that is A, B and C. Okay, 3 atom system. So each atom must having one pi orbital, and we are going to add it with dinophile or dipolarophile, sorry. So it containing a 2 molecular orbital system. So just go for this. We have to add HOMO of one system and LUMO of the another system. So just see, if we have this ABC system, suppose we have a dipolarophile, that is CH2N double bond N. Okay, that is a diazomethane. So CH2 means containing positive charge, nitrogen having one lone pair, and second nitrogen having one negative charge, right? So it is a 1,3 dipolar system we have, and suppose we have a dipolarophile, that is CH2 double bond CH2. Now you can see in case of this 1,3 dipolarophile, if we have to draw the FMO diagram, okay, our dipolarophile is CH2 double bond nitrogen, sorry, CH2 nitrogen double bond nitrogen. So CH2 containing positive charge, and here is the negative charge. Now you have to distribute this 4 electrons. We have 4 electrons, right? 1 2 3 4. So you have to distribute this 4 electrons, and in case of this dipolarophile, CH2 double bond CH2, 2 electrons. See, in case of FMO or FMO, for this dipolarophile you can draw, we have this 3 atoms 1 2 3. So there will be a 3 psi functions, psi 1, psi 2 and psi 3. Now in case of our last lectures, we discussed that the simple conjugated system containing non-bonding energy level will go from between the psi orbitals, and now if there is a condition which contains anions or cations or radicals, then that psi function will be divided by the non-bonding energy level. So here we have this negative charge as well as positive charge, so in case of this, non-bonding energy level will go from any psi function. Now we have this psi 1, psi 2, psi 3, as we have 3 atoms. Now for each atom will be one pi orbital. So see, okay, then we have to draw this. We have to distribute how many electrons? 4 electrons. So firstly, this psi 1 and non-bonding energy level will go from this. Okay, this is non-bonding energy level. Now you have to take a node. So psi 1 will have n is equal to 0, right? Then psi 2 have n is equal to 1, and psi 3 have n is equal to 2. So n is equal to 0 means no node, so all signs will be positive. Here we have to take one node, so this node will go from this orbital. Okay, in case of simple conjugated system, it will not go, the node will not go from any orbital, but in case of this system which contain negative charge, means anion, cation or radical, the node will pass from any orbital as per this. Okay, so now you have to distribute positive charge. As there is a node, the charge will be or sign will be changes. Okay, then in case of two nodes, 1 and 2, so firstly we have this positive lobe at upper side, this lobe will be changes. Now again there is a node, so there is a change in sign. So we have this FMO for this 1,3 dipolar system. Now we have to distribute how many electrons? 4 electrons. So 1 2 3 and 4. Now this is the HOMO for this system, that is a psi 2, and this one is psi 3 star is LUMO now. Okay, so we are getting this HOMO from this 1,3 dipolar system. Now in case of this ethylene molecule, which is our dipolarophile, Normally we have know that psi 1 and psi 2 is there, non-bonding energy level is there. So psi 2 star, we have 2 p orbitals, n is equal to 0, n is equal to 1, right? Psi function, what is the psi function? Psi 2 means n is equal to 1, so it's 0 node and 1 node. As 0 node, both signs will be same. In case of a 1 node, plus will changes to, okay. Then we have to distribute how many electrons? 2 electrons. We have 2 pi electrons, so distribute it in energy levels 1, 2, right? So this one is HOMO for our system and this one is LUMO. Now we have to do addition of HOMO of this 1,3 dipolar system. We have this 1,3 dipolar system and this is a dipolarophile. We have to add HOMO of this 1,3 dipolar and LUMO of this dipolarophile. Just go on addition. Our dipolar or 1,3 dipolar is this CH2 and double bond N. Okay, so I am taking that only C N, and this CH2 will have one orbital and this nitrogen will have one orbital, because from this middle nitrogen there is a node, so these orbitals are not taking part in the reaction, cycloaddition reaction. So suppose we have this type of system. Here is a positive upper side and negative, this positive is a downward side, so I am taking the same positive and positive. Okay, I hope there will be no confusion about this. And we have this dipolarophile LUMO. Okay, positive at upper side and negative at upper side. So if I just rotate this, you will get here positive and positive here. Okay, just this LUMO is the same. We have taken HOMO of this 1,3 dipolar system and LUMO of this dipolarophile, but the LUMO is psi 2 star. Here is the HOMO is psi 2 only. I am taking the same LUMO but just rotating this. This negative will comes here and this positive will comes here. Okay, now we can make a bond between this positive and negative. Easy bond formation is there. So you will get final CH2, right? This is a CH2, then nitrogen, as there is a double bond here. Double bond is here. It's remain as it is. So it is double bond. New bond will form between this CH, right? CH2 and CH2. So this is your final product, and it is a symmetry allowed reaction. Means reactant symmetry is maintained and the product at the product symmetry. So it is a symmetry. Here plus is there and minus is there. You can easily make a bond in the same phase. Symmetrical and symmetrical means there is a superficial and superficial addition. So it is a symmetry allowed addition. There is no superficial and intrafacial addition. Okay, so it is a symmetry allowed reaction. So in case of 1,3 dipolar system, it is a stereospecific reaction. Means as per the Diels-Alder reaction, if there is a compound having a syn symmetry or a stereochemistry, then product will have a same stereochemistry. So it is a syn addition. Then in case of examples, let's see one example. In case of this 1,3 dipolar systems, we are using this dipoles, that is A, B, C. This is a 1,3 dipolar system. So this 1,3 dipolar systems are stable system. Means some compounds are stable, like ozone we have. Okay, means oxygen. We have already seen this. This middle oxygen containing a lone pair. This oxygen will contain positive charge and it will contain negative charge. It may also undergo in a resonating structure. So ozone is a stable compound that we can use in 1,3 dipolar system. Also there is a diazomethane, right? We have already seen this diazomethane. You can say N double bond N carbon. Okay, this carbon will contain negative charge, this nitrogen will contain positive charge, and middle nitrogen contain lone pair of electron. Then second is suppose azides. Azides are also stable 1,3 dipolar system where it contain N. Okay, this nitrogen contain negative charge and this nitrogen will contain positive charge. So the azide, this type of systems are stable dipolar systems. And in case of some system which are unstable or they form in situ, means within the reaction, like ylides or imines. Ylides you are also already studying from Sanam. So ylides or imines or carbonyl oxides are just reactive intermediates. They form within the reaction. Okay, when the reaction is going on, they form as an intermediate and they are reactive also. So there are two types, that is some stable intermediates, that is 1,3 dipolar system, and some are unstable intermediates. So let's see one reaction. Suppose we have this type of system, CH3C, CH3. This is our dipolarophile, right? Alkene system. And we are going to add with ozone, oxygen, oxygen, oxygen. Now one oxygen will contain negative charge. This middle oxygen will contain lone pair of electrons, and this oxygen will contain positive charge. Now at the addition, the same type of addition means stereochemistry will remain same. So this electrons will make attack on this carbon, this electron will shift here and it will make bond with this oxygen. See, remaining structure as it is CH3, here is CH3, CH3, CH3. There is only just new bond formation takes place between this carbon and oxygen, this carbon and oxygen, and this oxygen remains as it is. So it is a 4+2 cycloaddition reaction. We are going this 4 electrons plus 2 electrons. So it is a 4+2 cycloaddition reaction. Suppose we have the another 1,3 dipolar system. Suppose system is like this. We have this hexene, cyclohexene molecule, hydrogen and hydrogen, plus we are going to add azide, N3. Okay. Now this oxygen, this nitrogen containing plus charge, this having lone pair, and this is having a negative charge. Then after reaction, simply this electron will shift here, this electron will make a new bond. So you will get finally product, whereas a new bond will form between this nitrogen and carbon, and this nitrogen remains as it is. And here, as it is a syn reaction, stereochemistry remains same. Okay, this is the final product. Then some reactions where these are the stable intermediates or stable 1,3 dipolar systems. Azides or ozones are stable compounds like this. And in case of unstable intermediates, means which form in situ within the reaction. Take one example of this. See, if we have reaction like this, suppose C6H5 CHO, we are going to add it within the reaction. So it is CH3 NH and we have this CH double bond CH2. So we have this CH double bond CH2 means alkane system. In presence of a hit, we will get this product, this type of product. See, pH, oxygen will be here, nitrogen will be here, remaining system as it is. So in this condition, in this state, there is a one unstable 1,3 dipolar system form, or yeah, if we have this condition, see C6H5 CHO, then after addition of this with this, okay, you will get, here is a CHO means you can see C6H5, we have this C double bond OH. This nitrogen can make a bond between this carbon and nitrogen, so you will get C6H5 CH double bond between this carbon and nitrogen, right? H2O will be eliminated out. Positive charge, this oxygen will contain negative charge, that is OH. We have already this, and CH3 on this nitrogen. See. Then finally, after resonating structure, we are getting here 1,3 dipolar system. See, C6H5 as it is, this CH, as this electrons if shift on this nitrogen, this electron from this one pi bond will shift on this oxygen, we will get here positive charge, right? As this electron from this pi bond shifting on this nitrogen, this CH will contain positive charge. Now restoration of electrons, that is lone pair on nitrogen, and oxygen having a negative charge. Here is CH3 remains as it is. Now this is our 1,3 dipolar system, right? 1,3 dipolar system, and we have in reaction, see, you can see reaction condition C6H5 CH double bond CH2. After addition of this C6H5 CH double bond CH2, you will get a final product, that is pH it is a 4 plus 2 cycloaddition CH3 pH. So as per this 4 plus 2 cycloaddition reaction takes place means 1,3 dipolar addition takes place. So in case of 1,3 dipolar cycloaddition reaction, the important point was we have one system which is 1,3 dipolar system containing A, B, C type of compound, where A containing 6 electrons at its outermost orbital and B and C containing 8 electrons, means completion of octet. This A containing positive charge and C containing a negative charge, and B must contain at least one lone pair of electron. Then in case of this all, A may be carbon, nitrogen or oxygen. This also carbon, nitrogen or oxygen in case of A and C. But in case of B, it may be a nitrogen or oxygen. If it is nitrogen, it can form a single bond or double bond. But in case of oxygen, it can only form a single bond in case of 1,3 dipolar system. Okay. Then in case of a 1,3 dipolarophile, it may be simple alkenes or alkynes or carbonyl compounds. Just addition of this 4 pi electron system, and in case of dipolarophile, it is a 2 pi electron system. So total it is 4 pi plus 2 pi cycloaddition reaction. Okay, and it is a syn selective reaction, as in case of Diels-Alder reaction also it is a stereo selective reaction. Stereochemistry will be remain same. If it is a cis, then it will remain cis. If it is a trans and reactant, then product will also get a trans. Okay, this is enough for 1,3 dipolar cycloaddition reaction. Next lecture we will see about addition of ketenes, cycloaddition of ketenes. Okay, thank you.